Hey guys, welcome to this integrated course on inferential statistics. This is part 1 of our full data science course. This full course has two main branches, statistics and mathematical modeling. Since these two areas have much to cover, I've divided this full course into smaller sub-courses that you can do at your own pace and only move on to the next one when you are more comfortable. That said, these are two main fields critical to your development as a data scientist. Both work hand in hand, and you need to be comfortable with both. That only comes with a better understanding and practice. Who is this course for? This course is for everyone in any field of mathematics, computer programming, machine learning, economics, finance, psychology, and the medical field in general. Statistics is a field of mathematics that helps its users make better decisions. When you gain a solid understanding of statistics, you will gain a technical ability to develop your own projects and will set yourself apart from everyone else, as this is the typical field that most people roll their eyes over and stay away from. If you choose to stick to it, this will be your advantage in the marketplace, as you will find the demand for it with almost no competition. With the rising demand for machine learning and artificial intelligence experts, statistics, mathematical modeling, and computer programming are the keys for you to becoming a specialist. Look at this like learning a new language. So, like anything in life, we'll start from the beginning. We will start from the ground up with no experience, learning the basics and fundamentals, and we will keep building from there, working our way together to more advanced topics. Again, our main goal is to help you gain the tools to develop your own projects. What will we address in this course? The first section is about an overview of inferential statistics. What is it? How do you use it? And the main terminology. From here, we will go through discrete and continuous variables. We will explain and solve cases together. Same thing for discrete and continuous distributions. We will go through the main ones from the binomial to the uniform and their sub-functions, the PDF, the PEMF, and the continuous distribution function called CDF, all with solved examples step by step. We'll explain and solve problems with confidence intervals, hypothesis tests, errors, and important properties. We'll work on one-way and two-way ANOVA exercises. And finally, we will work on examples to find estimators with MME, MLE, and OLS, and properties. I hope you enjoy this course. Let's start learning together. What is the purpose of statistics? Statistics is a framework to help users make decisions. When you are faced with a problem, what do? Well, you first analyze it, basically describing the problem. You then come up with an hypothesis to try and solve it. If it works, you solved it. And every time you face the same problem, you have a solution. This is important in statistics, as it means there is repeatability. The solution is accurate and you are able to reproduce the same results with reliability. If you didn't solve it, you gain feedback from the outcome and feed it back into your machine. You keep doing this process, adjusting your possible solution until you succeed. Statistics is about the same concept, about solving problems. It is a branch of mathematics that helps you make better decisions. There are essentially two branches of statistics. Descriptive statistics. Here we are collecting data, organizing it, describing it, showing it using graphs, and making conclusions, but without making inferences. Descriptive statistics can be useful to provide information about variables in a data set, highlighting potential relationships between variables. The most common descriptive statistics are graphical or pictorial methods to display data, and measures of central tendency, dispersion, and association. We will address descriptive statistics in more detail in a separate course, as this is too much information to cover for this one. For now, just keep in mind this main concept. With descriptive statistics, we are dealing with a data set, just analyzing it and drawing conclusions on it without making any further inferences. With inferential statistics, the second branch, here we are dealing with a sample from a population because it's too large, and making inferences from the sample to the population. What is the difference between a population and a sample? Let's say you have 50 people in a classroom. This is your whole study group. This is your population. You can make conclusions directly on this group, like the average grades, average heights, compare different groups in the same population and so on, and show all this information in a graph or tables. But what about if you want to know how many students from the whole campus like chocolate, and the college has 20,000 people there? Here, it's too many people for you to do alone, one by one. So here is where inferential statistics comes in. You gather a sample from the whole population, study it, and make inferences on the whole population. You reckon that the same 50 people in your classroom might be a good sample representing the whole entire campus. So this would be your sample. From here, you want to make assessments and generalize these to the whole university. 90% of these 50 people in this classroom like chocolate. Does this mean 90% of the whole campus out of 20,000 people like chocolate as well? Here is where some statistical techniques come into play to help us figure this out. In inferential statistics, there are essentially two ways to help us make inferences. The first one is estimation. Estimation is a process to help you get a direct value from the population. You want to know the population's mean, and you have the sample to work with. So you use the relationship between the mean from your sample and the population's mean and come up with the answer. Here are some things to know. Seen from the sample, an estimator is a formula to calculate an estimate from the population. An estimate can be either a point estimate, meaning a direct value like the population's mean, or an interval estimate, also called a confidence interval, where you state that the population mean is within a certain interval. Secondly, hypothesis testing. Here, we test a newly formulated hypothesis versus a standard hypothesis. We do this to see if there is a difference in the value of interest. Does this treatment work better than the previous one? We will get to these in more detail in a bit. Both the population and the sample have the same variables, but with different names and formulas. From the population side, we call these parameters. Here it's mean, standard deviation, variance, proportion, size. There are more, but these are the key ones. From the sample, we call these sample statistics, the equivalent to the population parameters. Here it's sample mean, sample standard deviation, sample variance, and so on. Notice how the letters are different. Some have a bar, others have a hat, others are capitalized. It's terrible, but it's a standard. So when you see one of these, it's important to know which one you are addressing, so you will know if you are looking at things from the population side or from the sample, as some problems have variables from both sides. Before moving on, a key point that is important for you to know right now is the right terminology. Let's talk about this for a bit so we can build a solid foundation. Without being clear on these terms, all questions and problems that you might ask and be asked about in statistics later on, it will start getting confusing pretty quickly, and there is absolutely no reason for it. We will solve this right here. The first thing to always ask yourself first is if you are dealing with a population or the sample. This is the first step. The second step is knowing what these terms mean. So let's get started. Big N is the number of data points in the population. The whole population consists of 20,000 people, so N, population size, is equal to 20,000 people, and N, sample size, is 50. Both are constants. From here on is about what we are trying to know, and none of the following variables are constants. All have a degree of variability because we are making assumptions, and any assumption introduces an error, either seen from the population side to the sample or seen from the sample side to the population. So because there is some degree of error in our assumptions, we are going to take this into further consideration when coming up with answers. This brings us to the first concept of measures of dispersion, called variance. What is variance? Let's look at an example. Let's say we have two funds and you invest $100,000 in each fund starting at 1st of January. At the end of the year, both funds delivered exactly 7% on point. We say that the mean for each fund is 7%. Throughout the year, Fund 1 had a peak of plus 15% and had a trough of minus 20%, but ended up at 7%. Fund 2, on the other hand, varied between plus 8% and plus 6% and also ended up at 7% as well. We say that Fund 1 had a higher variance in comparison to Fund 2, even though both ended up producing the exact same result. If we graph this, all this means is that the fund that varied more, its distribution has a wider variance, and our Fund 2 has a narrower variance, so it's tighter around the mean. What about standard deviation? What is standard deviation? In order to keep our calculations simpler, we do what is called a standardization. This process is also called unit conversion. Let's say we have the same calculation for a sample, but one of the researchers is from the UK and came up with the X values in pounds because they use the imperial system. The other researcher is from Portugal, and there they use the metric system. They both came up with the same conclusions, but one is presenting the X values in pounds, the other in kilograms. Do the end results change? No, but it's harder to read and make assessments between both. So we use what's called a standard deviation as a unit of measurement. Instead of showing the dispersion in weight, we show it in standard deviations from the mean. When we get to the distributions, we will do some calculations, but for now, just know that standard deviation is a way of referring to the same dispersion, the X values around the mean, but using normalized measurements. Mean, either seen from the sample or from the population, is the sum of all values by the size n. So in this case, 10 plus 20 plus 30 divided by 3, it's 20. In a more generic form, and we will need this later on in more complicated examples, it is the sum of all values, in our case from 1 to 3, divided by n. Proportion is exactly what the name implies. It is a proportion of the total value. Let's say 3 out of 8 people won. This leaves 5 of 8 people that lost. Frequently we need to compare proportions from samples. This sounds simple in the beginning, and I am re-emphasizing this as it starts to get more complicated later on. We will work through this together. For now, I just want you to understand the importance of getting clear on the terms, and if you are dealing from the population or the sample side, so that you can make the correct assessment and proceed with the right calculations. Let's continue with the terminology. There are two types of data: qualitative and quantitative. Under the qualitative type, sometimes called categorical, there are two types: nominal and ordinal. You can use nominal when there is no rank, like names John, Mary, or favorite colors like blue and red. Ordinal is when you have a rank, like first and second place, like and dislike. In the quantitative type, we have discrete data, when you can count, like number of marbles, people, balls, and so on. And continuous data, when you can measure, like a temperature or height. Here, there is a further distinction done called interval, when you have measurable data, but there is a difference between scales, like Fahrenheit and Celsius. We say it doesn't include an absolute zero because the scales are different. The last subtype is called ratio. Here we do have an absolute zero. Kelvin is measured considering an absolute zero. Height and weight are ratio variables because they also have an absolute zero. Let's move on. A variable is a placeholder. C equals 5. We say C is a variable that takes on the value of a constant, in the specific case, 5. You can choose any letter as a placeholder, but C can also hold the result of a function, not necessarily 5. Let's say you flip a coin. Your function computes the probability of the result being heads or tails, and your variable holds the result. You can say here that C equals the probability of getting tails in a coin toss. What about samples? Let's say you have a bag with 10 marbles. Random sampling is the idea of you taking a marble out of the bag without choosing any particular one. You are not choosing one specifically, you are taking one out randomly. The result you get, you assign it to your variable C. A trial or experiment, same thing, is you throwing a die. The event is the result from the trial. You got a 6. Independence is one result not influencing another. The die is evenly balanced. So you got a 6, but you could also get a 1 in the next trial. Each result, if the die is evenly balanced, has the same likelihood of occurring. You have 6 faces, so it's 1 over 6. A distribution is a function like a black box. You use this black box when you are trying to calculate a specific probability from the sample, and then extrapolate it to the population. We say that our x variable follows that specific distribution. We input the required values into the distribution and assign the output to our variable. Remember that we are not doing everything from the ground up. Statisticians before already came up with tools that can help you solve the problem you want the answer for. So the key here, first and foremost, is knowing which problem you have so you can choose the correct tool and compute the result. There are distributions available to calculate discrete and continuous experiments. We will go through these one by one in a bit. These distributions have some properties and also subfunctions that can further help us. On the left side, we have the probability distributions for discrete and continuous calculations. These functions provide a value. If we are dealing with a discrete distribution, we call it a probability mass function. If we are dealing with a continuous distribution, we call it a probability density function. On the right side, for both types of distributions, continuous or discrete, we have a cumulative distribution function. This is a subfunction that helps us calculate intervals because it keeps accumulating all probabilities until that point from the probability function. Let's look at the idea. First, keep this concept in mind. A probability always varies between 0 and 100%. Seen from the probability function, we are thinking about the individual probability. Seen from the cumulative function, we are thinking from 0% until that calculated probability. It's more of a mathematical tool to help figure out some values. For now, just keep in mind that probability functions, either discrete or continuous, provide an individual value. Their corresponding cumulative function helps us calculate more values to simplify our calculations. Mathematically, to go from the PMF to the CDF, we use summation because we are dealing with discrete value experiments, like choosing a red marble out of a bag with 10. To go from a PDF to the CDF, we use integration because we are dealing with continuous value experiments, like temperatures. We talked about distributions as black boxes that output a specific result as a solution. All distributions are functions. A function receives inputs. All probability distributions receive inputs like n, number of trials, x, number of successes, p, the probability of success, and more. Different distributions receive different inputs. This varies more with continuous distributions, as we are about to see. All distributions also have internal properties like mean, variance, and more, and in some instances we can do operations with different distributions. For now, just keep in mind what we have been developing so far. Let's keep this simple. You want to calculate a probability, you choose the correct distribution to help you solve it. You choose a variable to store the value from the distribution that calculates it. So your framework is x, random variable that can be either continuous or discrete, follows a distribution chosen as adequate to solve the specific problem. This distribution is also continuous or discrete. The distribution will receive inputs and will output a probability. X, your variable, stores this value so you can get your answer to the problem. You also have the corresponding cumulative distribution function if you need additional calculations. This is important, keep this in mind. I'll show you examples on how the cumulative function works later on. So let's look at some distributions and what they do. We use a binomial distribution when the outcome is binary, like succeed, fail, get heads, tails, get a specific card or not, get a specific side from tossing a die. The main framework here is either you get it or you don't. This is how you know you can use a binomial distribution. Let's go through an example. You throw a coin 6 times and you want to get tails 4 times. A coin has a 50% probability for each side. Just a note on representation. In most discrete distributions, you will see this representation part of the calculations for the distribution functions. Let's just go through this right now. You say n choose x, which is the same thing as saying n factorial over x factorial times n minus x factorial. This is also seen as n big C x. All this means the same thing. The calculations will have more elements, but this is the main part of it. I just want you to be clear on the specific element. So let's continue on. N equals 5 trials. You want x equals to 4 number of successes. The probability of succeeding is 50%, and the contrary to that is 100% minus 50%, which is in this case 50% as well. So the probability for this situation after the calculation, it's 23.44%. There is a special case of the binomial distribution called Bernoulli distribution, where n equals 1. Everything is the same, the only difference is that n equals 1. This means that in our example, you only throw the coin once and the experiment is over. So you throw a coin, the probability of x is equal to heads, and it's 50%, and the experiment is over. In both the binomial and Bernoulli, the number of trials is fixed. You throw a coin n number of times, like 1, 6, 10 times, and so on, until you get x number of successes. Here is different. You are calling people with a probability of 25% to book a meeting. You want to know what is the probability that 15 people must be asked before 5 say yes. Just like the binomial had a special case, here is the same thing. Instead of having 5 saying yes to a meeting, You want to know just for one. So, what is the probability that 15 people must be asked before one says yes to a meeting? Use the exact same formula, but notice that at the bottom from the previous formula, we now have 1 minus 1. In this distribution, we are interested in the number of discrete occurrences over a continuous space. Number of customers, discrete variable, entering a store within 60 minutes, continuous variable. Number of accidents in a road. Here it's the other way around from the Poisson. We are interested in calculating the probability of a continuous occurrence between discrete occurrences. Time, continuous, between two calls, discrete. Time that an integrated circuit lasts after 10 years. There is a special relationship between the Poisson distribution that is discrete and the exponential distribution that is continuous. Both share the same parameter, lambda. From the Poisson distribution side, the mean and variance are both equal to lambda. From your exponential distribution side, the mean is equal to 1 divided by lambda. Here it's called rate parameter. So if you see this term, you know that you are using the mean from the Poisson distribution and calculating the mean from the exponential distribution, which is 1 divided by lambda. This next distribution is a special case, as all values seen from the y-axis have the same probability of occurring. Back in the discrete distributions, we mentioned that the binomial distribution, where the outcome is a binary event, with the same likelihood of happening. Here is the exact same thing, but seen from a continuous perspective. So all we are doing here is essentially finding areas. This distribution is much easier to work with when you look at it graphically, so you can make your calculations because you can see it. You start by first finding out f of x, and then you will be asked about the probability of x being less than a value like we have here, where x is less or equal than 8, or here where x is greater or equal than 30, or here where x is between 10 and 26. We are always thinking about the area under the curve, in our specific case, a rectangle. So if you are asked what is the probability of x equals 20, the answer is 0. On the same logic, if you are asked about the value above the defined area, it's also 0, as it's outside bounds. Up until now, we have addressed some of the common distributions and how to use them. This last group that I've highlighted here has some unique characteristics that we are going to talk about. Let's start with a normal distribution. The normal distribution has this bell-shaped curve, also called Gaussian curve. This is a special distribution as mathematicians notice that under certain conditions, namely if the sample is large enough above a certain threshold, usually 30 samples, if you take a sample, find its mean and add it to a graph and repeat this process over and over again, the end distribution will start resembling the same bell-shaped curve. This is useful because they found they could extrapolate conclusions from most other distributions to the normal and get accurate results. So the starting point can be a binomial distribution or any other distribution, but we can use a normal distribution to solve the end problem. Just to reemphasize this point, all this means is that we can start with any distribution, and if it meets certain conditions, we can say it follows a normal distribution and continue from there. Because if you have at least 20 to 30 samples from the population, even if it's from a different distribution, its mean will be approximately equal to the mean of the whole population. Earlier on, we talked about the case where we had the same study, but one with pounds and the other one with kilograms. Both were normal distributions, but had different scales. From now on, take a note that we will address the normal distribution either by n or z. Both are referring to the same distribution, just in different forms. When we say z, we are saying specifically that we are using the standardized form of the normal distribution, where the values in the x-axis are in units of standard deviations from the mean, and not pounds, kilograms, or any other type of measurement. The t-student distribution is the normal distribution, but in a 2.0 version. A statistician in the 19th century wanted to use the normal distribution, but for smaller samples. So he came up with a modification in order to use it. You'll notice that when n starts getting large enough, the t starts getting close to z as well. So when do we use z and when do we use t? T is usually used for samples. In these two columns, we have a sample size below 30 and above 30. If we have a normal distribution with known variance, we use z for both. If we have a normal distribution with unknown variance, we use t for both. If we have a non-normal distribution with known variance, we use z if the population is larger than 30. If we have a non-normal distribution with unknown variance, we use t if the population is larger than 30. Notice one important point. N and t are both symmetrical around the mean. This is important because later on we can use the tables with this property. Normal and t distributions are used to build confidence intervals for means, proportions, variances, and so on. So for the most part, we use the normal for the population and t for the sample. In the exercise part of this course, we will use some examples when we know and don't know some population parameters. For now, just keep this in mind. The t distribution is more specific distribution based on the normal, but best tailored for samples. The chi-square distribution is used in hypothesis testing to compare variances. Here we are making assumptions on categorical variables and checking the difference between the expected value and the observed value. In theory, a coin has 50% for both sides in any amount of throws. In practice, most likely that is not what's going to happen. In two groups of 10 throws, you might get a result more skewed to one side than to another. So this test is highly dependent on sample size. From a mathematical perspective, the chi-square distribution, it is usually approached as a squared normal distribution. Two tests are usually done with the chi-square distribution. If you have one variable, the test is called goodness of fit test. The coin flip test is an example. If you have two variables, the test is called test of independence. Let's say you have 200 people that traveled to 4 different countries, and whether they stayed more or less than 2 weeks. So our two variables here are 1, number of countries, and 2, if people stayed more or less than 2 weeks. The F distribution is a ratio between two independent chi-square distributions divided by their respective degrees of freedom. We will use this later on for the analysis of variance when conducting hypothesis testing. Earlier on, I mentioned probability functions and cumulative functions. Let's look at this in more detail. Essentially, for each distribution, you have two functions available to you to solve the problem. If you want a value, you use the probability function. But if you want something like p with x less than between a range of values or above certain values, you can use the cumulative distribution function. This gets us to the use of tables. Let's look at the binomial distribution with n equals 10 and p equals to 45%. If I asked you, what is the probability of x being less or equal than 4? You need to sum all values from 0 to 4. Or just use the cumulative function that already has that computed result. Same thing if you need x less than 4, x greater than 4, or greater n equal than 4, same thing. This is where the CDF kicks in, and you can use it to solve these types of questions. With the normal and any of the discrete ones, in order to get the right values, there are some rules to remember. The last point to remember is that in order to use the tables when using the normal distribution, we need to always normalize and get the x values in standardized form. So if you have a problem where x follows a normal distribution with a mean of 750, and the question is, what is the probability of x being greater than, let's say, 700? use the same properties that we have been talking about by first normalizing it and now getting z instead of x, with a mean 0 and 1 standard deviation. Then we use the properties to deal with the greater than sign or the negative number. From the z table, we will get the answer. Now that we have an idea about the common distributions, let's talk about some concepts and putting those into practice. We'll start with the hypothesis testing. When we do an hypothesis test, we are literally doing what the name implies, conducting an hypothesis test. We want to figure out if there is a difference between the new tested hypothesis versus the default one. The default hypothesis is called H0 or null hypothesis. The hypothesis we are testing, it's called H1 or alternative hypothesis, same thing. We can have H2, H3 and so on. With hypothesis testing, we can compare any parameters like difference between means, difference between proportions, difference between variances. To do that, the procedure is 1. Define what we are hypothesizing. 2. Extract a sample from the population. 3. Find out the parameters we know from the population, so we can choose the right distribution. 4. Choose which distribution to use. 5. Conduct the test. 6. State the conclusions if there is a significant evidence for a difference or not. When conducting an hypothesis test, because we are inferring from a sample, we are by default introducing an error, as we don't have all the information, so our conclusions contemplate this error variable. Let's look at this in more detail. Look at the following table. The first column is the decision rule, either to accept or reject. The second and third column have either a true null hypothesis or a false null hypothesis. We call a type 1 error significance level or p-value, all mean the same thing, when we reject a true null hypothesis. And we call a type 2 error when we accept a false null hypothesis. The diagram below shows a more thorough examination. It is recommended to do this twice. The percentages refer to a significance level. Significance level is the percentage you are introducing as a type 1 error in your assumption. Let's say you conduct a test at 5% and reject the null hypothesis. You then conduct the test again at 1% and also reject the null hypothesis. The error is small and still rejected it, even at 1%. More grounded in reality, when making inferences about the population parameter, most likely your answer will be in a form of an interval, as we are introducing an error when providing an estimation. We refer to this as an interval estimation or a confidence interval, it's the same thing. So instead of saying the population mean is equal to 5, you reply with an interval, like the estimated population mean is between 3 and 7. When we are talking about confidence intervals, we are also talking about confidence levels. How confident are you that 5 is within the presented interval? You might say, isn't it better to have 100% certainty? The answer in theory, to be sure, is yes, but in reality is no. Why? Let's say you state, I am 100% confident that all students in this campus are human beings. This is correct. But in the majority of cases, you are introducing uncertainty, as you don't have all the data, like tastes and preferences. Can you be 100% sure that all people in college campus like chocolate? The only way for you to know that is that if you ask everyone. So here, because we are dealing with a sample, we are doing an inference. We are making an extrapolation from the sample to the entire population. In our specific case, from 50 people to the whole college campus of 20,000 people. We do this because it's not practical to use all the people in the population. We are knowingly introducing an error, and we have to state it. We are saying that in a smaller interval, we are X% sure that the population parameter is there. Not 100%, but a certain degree of certainty. Now that we know about hypothesis testing and estimation, let's focus on this last part on the estimators. An estimator is the function you use to get to the population parameter. And from the previous slides, we know that we are introducing an error. So the quality of the estimator is in itself a field of study. Let's look at this in more detail. We say an estimator is unbiased when it's centered. Same like we were talking about with the normal distribution and the t-distribution. So when you add the bias, if it's greater than 0, it means the estimator is positively skewed. If it's 0, it means it's centered because there is no bias. And if it's less than 0, it means the estimator is negatively skewed. The second property of an estimator is efficiency. We say that an estimator that has lower variance is more efficient. Remember when we're talking about confidence intervals? If we have a tighter variance around the mean, that means the estimator has lower variance, it's more efficient. The third property is consistency. This means that the limit when x tends to infinity of the expected value of the parameter will be the parameter, and that the limit when x tends to infinity of the variance will tend to 0. All this means is that ideally we want a parameter that is centered and with little to no variance. In reality, that's not what happens. So this is what's called bias-variance trade-off. Let's look at this graph. We have data points gathered from the population. These are our sample. So there is a degree of representativeness from the population in our sample data. And we are trying to come up with a model that can accurately predict a specific parameter from the whole population. If there is one takeaway from this whole course that I want you to remember is this concept. We are making an assumption and comparing it to the observed reality value. And because we are using sample data, we are introducing an error. So all the mathematics, models, it's going back to the drawing board and getting more accurate about reducing the error. It's all about optimization. We have an expected value and we have an observed value. So we are trying to reduce the difference between both. The first one is called OLS. We start off with a set of data points and we are trying to find the y-intercept and the slope. Earlier in mathematics, you were most likely taught the equation of a line as y equals mx plus b. Here it's the exact same thing, but we are adding an error. Here x is alpha, b is beta. Same concept. The only difference is that an error is added. The idea here is to minimize the distance between the expected value and the observed value. To accomplish this, we differentiate the equation for the line and equal it to 0 in terms of alpha and then for beta. The idea is when you are trying to find a maximum, minimum or inflection point in a function, you find where its derivative is equal to 0. You might have only one equation line to work with or several, but the concept here is the same. Don't get too bothered about the math, as this is for you to understand how it works. Most likely, you will be using Python, R, SPSS, or any other software to do the calculations, but it's important to know how it works. Then you can leave it up to the computers. With this technique, we use the normal curve to find the best fit for the data points within an interval. It's a different way of approaching the exact same problem. Because of its unique shape, the highest point represents where most data points are centered. So by finding the derivative and equaling it to 0, we are finding the maximum of the function. The last method is called method of moments. We want to estimate the population parameter, but here is done differently. It's more mathematics and less with a graphical concept. We use what's called a moment generating function to find a specific function for the distribution we are studying and get the mean, variance, and so on. Let me show you. Notice the correspondence from the sample to the population. Each m is called moment. First moment, second moment, and so on. Nothing to do with mean, variance for now. Think about it as just m1, m2, m3, and so on. These are the formulas used at each level to go from the sample to the population or from the population to the sample. Just note that each side has its corresponding function. The moment generating function is given by the expected value of e to the xt. The first step is figuring out which data type is your distribution, if it's discrete or continuous. Let's look at an example. With a Bernoulli, we have a discrete distribution. So we use the probability mass function and multiply it by e to the xt. Since we have two outcomes in a Bernoulli, remember that n is equal to 1, so you throw the coin once and the experiment is over. So since we have two outcomes, either 0 or 1, we add both and get 1 minus p plus p times e raised to the t. This is our moment generating function. To get our first moment, we find its first derivative and plug in 0 for t to get p. To find the variance, we need e squared. We need the second moment. To get that, we differentiate the function again and plug in 0 for t again to get p again. So our variance from the formula is m2 minus m1 squared. In other words, p times 1 minus p. Let's look at another example for a continuous distribution. Same process. This one is continuous, so we use the integrating function in terms of x and multiply by e to the xt and get the moment generating function, lambda over lambda minus t. The first moment is the first derivative. Again, plugging in 0 for t, we get m1. Second moment is the second derivative. Again, plugging 0 for t, we get the second moment, m2. The variance is the second moment minus the first moment squared. So we get 1 over lambda squared. And there you have it. You have just completed the first part of the course. In the next part, we'll focus more on solving exercises. A one-way ANOVA compares 3 or more than 3 categorical groups to establish where there is a difference between them. Within each group, there should be 3 or more observations, and the means of the samples are compared. So it's like a bucket that has a bunch of observations inside. In our specific case, here each column represents the time each salesperson spends on the phone in any given day. Salesperson A did 6 days, salesperson B did 5 days, and C did 4 days. Step 1, you count n for total and for each. So A is 6, B is 5, C is 4. So n, you just add those up and get 15. And then you find the average for each one. So you get all the values, and the total average value is 52.57. Step 2, usually you will be given some data. If not, let's do this from scratch. You'll need to find 3 things: sum of squares, total sum of squares, and factors. The sum of squares is found by squaring each number. This will give you this value. Then we'll calculate what's called the total variation by subtracting n times the total average squared. So we get this value. Factor A is found by multiplying 6, 5, and 4, which is the number of days for A, B, and C. It's the average of each one minus the overall average squared. The next step is to enter the degrees of freedom. We have 3 rows, so the degrees of freedom are 3 minus 1 equals 2. Step 3 is to complete the table. We start with the degrees of freedom. So we have the total sample, which is 15. So the total degrees of freedom is 15 minus 1, which is 14. Factor A is 3, so 2. And we do the difference to get 12. We calculated the total variation, and we know factor A. So the residual is the difference. Mean square is 794.23 divided by 2. Same thing for the residual and for the F statistic. The F statistic, you divide 397.12 by 93.65 to get 4.24. Step 4. Go to the F table at 5%, at 2 and 12. The entry that you'll find is 3.885. This is your critical value. This is the cut-off point that separates the null from the H1 hypothesis. Since 4.24 is in the H1 region, we reject the null and conclude that there is evidence of a difference between the time salespeople spend on the phone. A two-way ANOVA is like a one-way ANOVA, an hypothesis-based test. However, here we have another variable. Let's say we have 5 stores and we have 3 periods, morning, afternoon and night. The values in the table are the average number of people in each store and in each period. So let's say each column represents the 5 stores from A to E, and each row represents morning, afternoon and night. The values represent the average people number in each store during each period. Step 1. Add the marginals to the table and find the averages. Confirm if you are correct with the cross value, total average. Step 2. Find total sum of squares, factor A and factor B. Same as before. Total sum of squares is sum of squares minus n times the total average squared. Factor A is number of columns times the square difference in the marginal rows, top to bottom. Factor B is number of rows times the square difference in the marginal columns, left to right. Step 3, just like before, is filling in the table. We start with the degrees of freedom, so it's always -1. We do that for factor A and factor B, and the total. And the residual is the difference. Let's move on to the SS column. A is 680.93, so mean squared, you divide by the number and you get 340.47. Same thing for B. Residual is the difference between the total and factor A and B. So F for factor A is 6.43 and F for factor B is 3.57. These are your critical values, the cutoff points between the null hypothesis and the test hypothesis. So same as before, we go to the F table, find the one with 5% and for factor A, look for 2 and 8 degrees of freedom. You'll find 4.459. Since our test statistic is in the H1 region, we reject the null hypothesis and state that there is evidence for a difference in the time spent in each store. For factor B, same as before, go to the F table, find the one with 5% for factor A, look for 48DF. You'll find 3.838. Since our test statistic is in the null region, we reject the H1 hypothesis and state that there is no evidence for a difference in the time of the day spent in each store. In this problem, we have the expected value of x that is equal to 1/3. We are given a PDF function and we are asked to show that a equals -2 and b equals 2. And the second problem is to compute the variance. So let's get started. We need to go to the CDF so that we have all the cumulative values until we reach 100%. This is an important rule to always remember, that any probability is always between 0 and 1. So what we are doing here is going from the PDF to the CDF. So from 0 to 1, we're going to integrate the function. So this is the same thing as saying the integral between ax plus b dx equals 1. This is the important part, because it's a CDF and it's a cumulative function to all the values, and we know that it goes from 0 to 1. So our CDF is equal to the integral of a 0 to 1 x dx plus b dx equals 1. So next step, let's continue. So a x squared over 2 between 0 and 1 plus b x from 0 to 1 equals 1. So let's continue. So this one with 1 and 0, so this is a 1.5 plus b equals 1. To find the expected value, remember that it's the integral of the function times x. So this is the expression, and explicitly here we are told that is equal to 1/3. So when we solve the expression, this is what we get. So it's the integral between 0 and 1, x, ax plus b dx equals 1/3. So let's continue. So it's the integral between 0 and 1 of ax squared dx. We're just splitting the integrals using, since we have the sum here, plus the integral from 0 to 1 bx dx equals 1/3. So let's continue. So ax to the third power divided by 3 between 0 and 1 plus b x squared divided by 2 equals 1/3. So let's continue. So this is the same thing as having 1/3 a plus 1/2 b equals 1/3. So this is our expression, since we already told that expected value of x is equal to 1/3. So since we have two expressions, we are going to use both and solve the system in order to find a and b. So let's do that. So the first expression is 1/2 a plus b equals 1 from the CDF, and the second expression that we have just found is 1/3 a plus 1.5 b equals 1/3. So this is the system, and we're going to find the values for a and b. So let's do that. So we can get b on one side and the rest of the expression on the other side. And on the bottom one, we can substitute the values. So 1/3 a plus 1.5. Now we get the full expression there. So it's 1 minus 1/2 a equals 1/3. Let's continue. So now we have 1/3 a plus 1.5 minus 1/4 a equals 1/3. So now we get a and all the elements for a. We have two elements here, so we're going to get the elements inside. So it's 1/3 minus 1/4 equals to 1/3. And then we get this guy to the other side, so minus 1/2. So if we substitute the values, divided by 12 is equal to minus 1/6. And this is the same thing as saying that a is equal to minus 2. So now that we have this value, we can go back here and continue the expression. So b is equal to 1 minus 1.5, and now minus 2. So b is equal to 2. So this one goes here, b equals to 2. So we now have both values and confirm the given values. So a equals minus 2, b equals 2. We have the expected value that is equal to 1/3. So all we need to do now is find the variance of x. Remember from the previous theory model that the variance of x is the same thing as saying the expected value of x squared minus the expected value of x, all this squared. So we have this value and we can square it, but we are missing this one. So to find that one, we're going to use the same expression again, but instead of x, we're going to do x squared, and the rest is the same, f of x dx. We're going to get the integral between 0 and 1 of x squared, and then the expression on the inside, so ax plus b dx. Let's continue. So a comes outside, and then we have x4 divided by 4 between 0 and 1 plus b x3 divided by 3 also between 0 and 1. So continuing on, so a 1/4 plus 1/3 b. Then this is the same thing, since we now have the values here from this one and from this one. So all we're doing here is substituting the values, and we're going to get that it's minus 2 divided by 4 plus 2 divided by 3, which is the same thing as saying plus 2 divided by 12, so 1/6. So our ex squared is equal to 1/6. And now we can substitute the expressions. We have this one, we can square this one, and we're going to get the variance. So the variance of x is equal to the first element that we have just found, so it's 1/6, minus 1/3, all this squared, and this is going to be equal to 1 divided by 18. Hey everyone, in this video we are going to go through interval estimation for variances of a normal distribution. There are several types of confidence intervals that you can build, but this is a specific one I want to go through because it generates a lot of confusion with people, especially in the denominator part, and I want to go through this because you can solve this. So let's go through this. So this is the formula, there's no brainer. Essentially you have this lefter part and you have the righter part, so the parameter will be between these two values. The top part is pretty simple, so let's say we have some values. Let's say it's n, it's equal to 15. Let's say the variance is equal to 24.5. And now let's get into the gist of it, and the significance level is equal to 5%. So let's focus first on the part that presents a little bit more challenge so that we can do these on a regular basis. So let's get to this. So the way for you to know the type of confidence interval is by looking at the significance level. Because this is 5%, this means that the confidence interval is 1 minus 5%. So this is the same thing as saying that the confidence interval is equal to 95%. So now that we have this out of the way, we know that we are building a 95% confidence interval. The second part is finding out which values that we get here at the bottom. You start with the significance level, we know that it is 5, and you divide it by 2. And you're going to get two parts. The bottom part is 5 divided by 2, which is the same thing as saying 2.5. And the other part, it's 1 minus 2.5, so we have 97.5. So we build the graph and we divide it into the appropriate section. So this one is 2.5, this one is 97.5, and this one in the middle is the confidence interval. So the values that we are going to find for this one and for this one, it's f, I'm going to write this here, f 2.5 and 14 degrees of freedom. And this second one is 97.5, 14 degrees of freedom. You look those up and you have your denominator. Let's say now we have n equals 9. The sample variance is equal to 72.76. And the significance level is equal to 10%. So again, it's 1 minus that. So we know that the confidence interval is 90%. To find the values, so we're going to divide the significance level by 2, and we're going to get the lefter part, so 10 divided by 2 is 5, and the other one is 95. So when we build a graph, we start with the middle part, we know that is 90%, the left part is 5, and the right part is 95. So when we build the confidence interval, so we get the big brackets here, and it's 9 minus 1, the sample variance squared, divided by, and then let's just get the top part first, and then 72.76 squared. And now let's get to the important part. So the values that you're going to look up is 5 and 8, because it's 8 degrees of freedom. And then this is equal to 15.51. And the same thing for this one. So we found that is 95 with 8 degrees of freedom, and if you look this up, you'll find that it's 2.733. So all you have to do is the math between the numerator and denominator, and you're going to present the confidence interval with both values. I hope this helps. And that's it for this course. I hope this helps you guys out. If you have any further questions, let me know so I can help you.